Now, if we're going to work with standing waves, well, if the standing wave is, well, either air in a tube, or perhaps a wave on a string, or something else that we could conceive of, then if both ends count as open, or both ends count as closed, then the wavelength that fits on that will be given by 2L divided by m, where m in this case could be any integer, 1, 2, 3, 4, etc. The frequency then is equal to the speed of the wave divided by the wavelength. So the frequency of that wave will be given by m, 1, 2, 3, 4, etc., times the speed of the wave divided by 2L, or I could take that, find that frequency where m is equal to 1 and define that as the fundamental frequency. So every frequency after that would just be an integer, 1, 2, 3, 4, 5, whatever, times that fundamental frequency. If I've got a case where whatever's holding the standing wave or propagating the standing wave is open to one end and closed to the other, then it's different. We've just looked at, we looked at the last section. We're looking at learning objective 21.3. That this length of that tube then, the smallest tube, will be 1/4 of the wavelength, not 1/2. And also consider that we cannot have a tube that is exactly half a wavelength or a full wavelength long won't work in this case. If I have a node and a node, or an antinode and an antinode, that's not going to work for an open-closed situation. So I've got this works with integers, but it's every odd integer, 1, 3, 5, and so on. Now let's look at an example. Suppose I have a tube, and that tube has there's a variety of different speakers. Not universally, because we're not hearing all the harmonics. But I put my ear to it or take a microphone here, and I determine that two waves that are really showing up strongly. Therefore, two waves that have standing waves inside that tube are at 3,450 hertz and 4,600 hertz. Now, what this is telling us is that, okay, they're the same wave, sound, in the same substance, air, in the same tube. So they both fit, well, open at both ends, they both fit that these two frequencies are each some integer times some base frequency. Now, could this be one? Well, if that's one, then if that 3,450 hertz is the fundamental frequency, then the next frequency that resonates there will be at 6,900 hertz. So the 4,600 hertz will not be heard. It's a way of finding out now which one of these which way does this fit? I'm just taking you through one way. Use the way that works best for you. So if I look at this, okay, suppose that were m equals 2. Well, if that were m equals 2, in that case then, the fundamental frequency would be 1,725 hertz, which means that I would have resonances at 1,725 hertz, 3,450 hertz, 5,175 hertz, but not 4,600. So that one's not true. If this turned out to be n equals 3, then, if that turns out to be n equals 3, okay, then the fundamental frequency would be 3,450 divided by 3, or 1,150 hertz, which means that I would find resonant frequencies at 1,150 hertz, 2,300 hertz, 3,450 hertz, and at n equals 4, 4,600 hertz. So this one is one that can work. Now, because these are multiples in there are other ways to find things out. If for some reason you had ended up in a case where you had said, well, what about it where n equals 6 and n equals 8 here? Okay, it turns out that that works. If I were taking that, if this is a face-to-face class, I have to accept that. If this is an online course, then go with the smallest possible case because the automated assessment tools, Master in Physics or web work, whichever we have to be working with at a given time, will be much pickier and you cannot resort to reason. So, if we take this case, where that case works, then I know that my fundamental frequency then is 1,150 hertz, which is equal to 345, the speed meters per second, over 2 times the length of the tube. That gives me a length of the tube equal to 345 meters per second divided by 2, and that divided by 150, 1 over seconds, which cancels out, or a tube length of 15 centimeters. Hopefully, that is a useful example.